okay, or not continuous, and then differentiable or not differentiable, and we need to state why. You can't just say yes or no. All right, so you're given this graph. You have no idea what the function is, and what we want to do is just to determine if the function is continuous or differentiable, and if it's not, we need to state why. All right, so at x equals 0, is the function continuous? True or false? True. Okay, basically, at 0, I could sketch this graph without picking up my pencil, right? Okay, so now let's look at differentiability. Is the function differentiable at x equals 0? Why? Perfect. Okay, so again, vertical tangent line. You should recognize this, some of you. VTL. All right, let's take a look at x equals 2. Continuous, yes or no? Yes, true. Differentiable. Why? Absolutely. We have a cusp. X equals 3. Continuous? True. Differentiable? True. Okay, x equals 4. Continuous? False. Why? Okay, we have a jump discontinuity. All right, now here's the thing. If I asked you to prove to me that this was a jump discontinuity, do you know what you need to do? Yes. The limit, but it's not just the limit from the left and the limit from the right. What else do you have to? F of, in this case, f of 4. Okay, perfect. Okay, and then differentiable. No. False. Same reason, right? Jump discontinuity. Okay, questions? Yeah, I don't like the next problem, so we're skipping it. I just don't like it. It's a terrible problem. Okay, so far, we have been going from a function to the derivative. Now what's going to happen is you are given the derivative, and you're going to need to go backwards. So we have two different formulas, which are really actually similar. So this is why it's called the definition of the derivative reversed. So we're going to look at two things. We're looking at the definition of the derivative based on what we know, are most familiar with. So it's right here. What we know this as is f prime of x. F prime of a just represents, we know that point. We know the a value. Okay, and this is as h approaches 0. You could also see it as delta x. Or version 2 is f prime of a. Okay, and this is actually where you're plugging in that value. Okay, so how do I know which one I'm using? So I'm going to talk about that right now. If I'm using definition 1 or 2, when you're looking at this, this is the person had the function, they had the a value, and they plugged everything in. If you are given as h approaches 0, or you see this has an h, this is going to be definition number 1. Whenever you see an h anywhere, okay, so look at B. Is that 1 or 2? It's definitely 1 because you have the h. Okay? This right here, 4 plus h, is what replaced x. So if you take the 4 plus h out and you put in x, what is the function? It's x squared. So f of x is equal to x squared. Take this out and put your x back in there. Because this says 4 plus h, the quantity squared. This right here is your a value. So then what they are finding here is f prime of 4. Let's do it again with B. Look at B. Okay, we already said that it's 1. Take what's inside with the h and take it out and put the x in. What is the function? 2x cubed. What's your a value? 5. 5. Okay, let's jump to see where we don't have an h. Let's take a look at D. Okay? When I look at D, this right here is your function. This is f of x. So I have f of x is equal to x squared. This is version 2. Right here, this number, this is your a value. So now we have a of 2. So this is f prime of 2. What was this right here? This is f prime of 5. So take a look at f. So tell me which one this is, 1 or 2. This is 2. What's the function? F of x is 1 over x? It's 2 over x. That whole thing is your function. It's 2 over x. What's your a value? It is 3. Okay. You guys have a couple of problems in your homework where you have to do something similar to this, so I want to show this to you. So there may be some occasions where you will be asked to prove that a function is continuous and not differentiable, okay, or continuous and differentiable. So this is a two-part problem. So the first thing I'm going to do is basically review continuity with you, because we just talked about it. Jay told us about it. So here we're looking at continuity. Okay, and this is where we have to evaluate, in this case, the limit as x approaches 1 from the left of f of x should be equal to the limit as x approaches 1 from the right of f of x, which should be equal to f of 1. Ooh, that's crooked. All right, so first thing we want to look at is the limit as x approaches 1 from the left. Which equation am I using, top or bottom? Top. So this will be x squared plus 1. So then what is the limit as x approaches 1 from the left? It is 2. Okay? All right, from the left. So now we want to look at the limit as x approaches 1 from the right, which means we're using the bottom. What do we get? We do. We get 2. Okay? And then f of 1 is equal to? Yeah. I mean, you kind of already did it, but you still have to show. Okay? So we would just say, therefore, f of x is continuous at x equals 1. All right, continuity proven. Check? So if the function is continuous, it can be differentiable. Can be. But graphically, what if this was a cusp? So we need to prove differentiability from the left and from the right. All right, so that's what I'm going to do. And in doing this, I'm actually going to use the second definition up at the very top, so I'm going to write it down. So I'm using formula number 2. We're using the limit as x approaches a, which in this case is going to be 1, of f of x minus f of a over x minus a. They gave us a. It's right here. It's 1. Okay, so basically what you have to do is prove differentiability from the left and from the right, because this is a piecewise. We have two different functions. So we're going to evaluate the limit as x approaches 1 from the left, and now I'm plugging in here. F of x from the left is what? I'm pointing to f of x from the left. Which one? It's either top or bottom. Top. X squared plus 1 minus f of 1. What is f of 1? It's 2. We found it already. Over x minus 1. Okay, so I plugged in the function, I evaluated f at 1, and then I plugged in 1. So this becomes x squared minus 1. We have the limit as x approaches 1 from the left of x squared minus 1 over x minus 1. Problem here, direct substitution, I get 0 over 0. But do you see something that I could do that might help me? Absolutely, I'm going to factor. The limit as x approaches 1 from the left of x plus 1, x minus 1, over x minus 1. These are gone. So this is what I have. Can I use direct substitution now? Yeah, what do I get? 2. Okay. So far, continuous, 2, 2, 2, differentiable at 2. So I'm hoping that from the right I'm going to get 2. Is it possible that I might not? Sure, anything's possible, right? So this is how you do it from the right. It's the limit as x approaches 1 from the right. Okay? What's my function from the right? 2x minus f of 1, which is 2, over x minus 1. What should I do? Just factor? Limit as x approaches 1 from the right, 2 times x minus 1 over x minus 1. What happens? Gone? I get 2. So here you have the limit as x approaches 1 from the right of 2. How do you take the limit of a constant? It was a rule. It's one of the ones you guys wrote on your card. The limit as x approaches any number of a constant is the constant. Continuity proven. Differentiability proven. You're done. If you get different values, I think one of your homework questions says, prove that the function is continuous. Check. Prove that it's not differentiable. These would be different. Or something would happen. Maybe you would get infinity, or you can't, it's indeterminate. You can't define it at all. Questions? Are you sure? Okay. You need to have your calculators out.